All right, good morning. It was a beautiful tribute. Thank you. My name is Tammy Richardson. I'm at the University of South Carolina, but here I'm have the honor today of introducing our plenary speaker, Dr. David Moffat. David did his Bachelor of Science degree at the University of Edinburgh in computer science and artificial intelligence. He did a master's and a PhD degree both at Queen Mary College in London. And he is well known for using artificial intelligence approaches in his research, and that's what he's going to talk to us about today. Now, I tried to get some inside information on David because it's kind of boring to read the usual stuff, and I asked him, well, what do you like to do in your spare time? And it took a really long time answering that question. So I think he probably works a lot. He did tell me he likes to sail. So I'm going to couch this as two truths and a lie. And you have to figure out which one is the lie, but you can ask David, don't ask me. David likes to sail, he likes to drink Chardonnay on the beach, and he likes to rock climb. It's your call. Today he's going to talk about artificial intelligence, and with that, I will introduce you to David. Thank you.
Thank you. Thank you very much for the introduction. So this works, great. Hello, my name is Dave Moffat. This is my first ASLO event, so I'd like to start by thanking the organisers for inviting me. And I really look forward to meeting you all and hopefully learning a lot from you. But I thought it would be interesting today to talk a little bit about my background in machine learning and some of the challenges and opportunities that I've seen within the aquatic sciences environment. To go into a little bit more detail on the introduction, I am a computer scientist by trade. I am an AI machine learning data scientist at Plymouth in the UK, right on the southern tip. And I lead on all of PML's AI and machine learning activities. But I am a computer scientist. I've studied artificial intelligence and I've followed that career trajectory. So please go easy on any of the complicated aquatic science questions. I'm not the expert for that, but there are several others who may be able to answer any of those questions. But why talk about AI? Why talk about machine learning? There's a couple of graphs that I pulled out that I found which talks about how these things have been growing in a few different domains. And I'm not claiming any of them are perfectly right. I'm just using them as a demonstration. But one is the fact that there's a growing curve, an exponential curve within deep learning papers, certainly in physical oceanography. This seems like quite an interesting trend, probably not surprising if you've paid any attention to the news in the past 5 years about the fact that people talk about AI all the time. But the one that I think is more interesting is that there was a paper that came out a few years ago that talked about the impact of AI on a whole series of different sustainable development goals. And I think this one is more interesting across the board because it acknowledges, first of all, that AI doesn't solve all the problems, and it also acknowledges that AI actually can make things worse. And I think that's a really important thing to remember, and I think it's a really important thing that I need to tell myself every single day I go to work. Just to go into a little bit more detail, particularly on the life of water, I don't know the details of what these sustainable development goals are, and I've certainly not memorized them, but there's some evaluation based on this paper. I encourage you to go away and read it. Again, I'm not saying I completely agree with all the results in this paper, but I think it tells a good story, and I agree with the points that they're making, which is the fact that there are some things that AI can definitely make worse as well as make better. But on average, it can make more things better than it can make things worse. So with careful use and with consideration, we can use it to our benefit. But that doesn't really answer the question of what is AI. I think it's important because lots of people will come from very different contexts, have different ideas, and this is one of the places that I quite commonly like to start when I talk about AI in a marine environment, in an aquatic environment. Because there's a lot of buzz, there's a lot of hype, there's a lot of press and corporations trying to sell you things. And so I think it's really important to just start from the beginning so that I'll tell you my definition and then we can go from there. So artificial intelligence is a large field of computer science research. Originally born out of cybernetics, started in Dartmouth College over here in the US. But broadly, it is trying to create something which looks like it can mimic some sort of intelligent behavior. And as humans, we like to attribute intelligent behavior to intelligent humans. So something that looks like it's doing something clever. Nothing more, nothing less. You can write some very complicated if statements in a piece of code, and then you could brandish that as AI if you wanted to, so long as it looks like it's doing something clever. Within that, you have the field of machine learning, and that's really where I focus on a lot. That's also the thing that has really been exploding in the past few years. And machine learning is a particular type of AI in which we are using data. So it's a very data-driven approach, and then you use stats to try and understand those data to then produce something that can repeat. So it's a fully data-driven method. And within that, again, we have this domain of deep learning. And deep learning is a subset of machine learning where you are building bigger, more complicated models, typically with neural networks, where you will layer complex structures of neural networks together to try and learn some sort of detail. And so when people talk about AI, it's a very, very broad thing, and machine learning is very much a data-driven thing. So machine learning is learning from data. So the sort of traditional approach when you write some code is you take some data, you have a program, and then you put them all together into a computer, and then you'll get some sort of output, which is great when you know exactly what you need to do and you just want to process your data in a very deterministic way. The machine learning paradigm is, I have a big bag of data, I know what my output wants to be, but I don't necessarily know how to get there. So yeah, computers being able to learn without being explicitly programmed, it's essentially taking the data and learning from those data. Which means that you live and die on the quality of your data. And that can allow us to do lots of really interesting things. I've written marine science here. That's because I use marine science and aquatic science interchangeably, which is incorrect. I am aware of that. So I'm acknowledging my own bias and my own background. That was a mistake I made. So if we just roll with it, I'll not talk about it again. So machine learning allows us to analyze massive volumes of data. Massive volumes of data that we cannot possibly go through manually. We can't process that quantity of data, so we need some more complicated tools. It allows us to start looking at how we might move things between different domains, fuse all our data together in different ways. So this could be trying to combine different sensors together in different interesting and unique ways. It allows us to automate the monitoring. One of my mantras when I build an AI system is, what am I going to build the AI system to do? And the first thing is automate the mundane. If there's something that you're doing day after day and you think there must be an easier way to this, we can look at automating some of those processes. It can optimize for solutions. I've seen a couple of really interesting papers recently that talk about going and selecting sample sites based on some model data and then AI to predict where we have larger uncertainties. The benefits of this are there's an entire ocean to sample, and we could either sample the bits that we know something about, or we could find other ways of exploring where we need to sample, where the largest errors are, where the most confusion is. We can build models to predict and to forecast. I'm not saying this is the only way to do all these predictions and forecasting. There are definitely some very complicated physical models that understand all the physics, understand all the biogeochemistry, and can produce amazing forecasts. But there are things that we can't use them for, and I think it's important to see what we can do with that. And we can create real-world simulations. So these sorts of simulations, people talk about digital twins quite a lot, and I think AI can really help and enable us to explore what these digital twins can achieve and to enable them to explore new domains. But this also brings a lot of problems. This brings a lot of challenges. First of all, in how do we achieve any of these things? How do we build systems that people actually trust? Because I think there should be an inherent distrust in any of these systems. I think you should distrust the first results you get. I think as scientists, we owe it to ourselves and we owe it to our community to distrust every result we have until we've verified it. You can also easily misuse these tools. You have, you have to make sure that they are reliable and you can interpret what's actually happening. So there are a lot of challenges as well. So to go back to the other side of it, there are some domains that are really, really appropriate for machine learning. So what is a good machine learning problem? There are a lot of domains where human expertise just doesn't exist. We don't know why something works. We don't know how this process happens, but we have lots and lots of data that represent that problem. So that's the ideal scenario for some sort of machine learning thing. We don't understand all the processes, but we can measure it. Or humans can't explain their expertise. You might have a human that can look at some data and make an interpretation, but the moment that you try and build that into some sort of statistical model, the results are never as good as the human looking at those data. So the really classic AI one in that domain is telling the difference between a cat and a dog, because the internet loves looking at pictures of cats and dogs, but to define a mathematical formulation of the difference between a cat and a dog is almost impossible. But every single person can tell the difference. Models must be customized. Again, I'm going to borrow something from outside of the aquatic sciences domain here. I use a music app called Spotify. I think the US equivalent is Pandora. Or Spotify as well. Great. Fine. So I use Spotify, and every single day I log in, it comes up with a bunch of recommendations to me personally and says, oh, this is the music you should be listening to today. I don't think it would be possible for them to have enough people sitting in their offices looking at everything I've listened to in the past 3 months and then saying, oh, this is what you should be listening to tomorrow. Oh, I've listened to this new thing and Dave will love this song tomorrow. And I don't think it would be reasonable to do that either. So trying to build some sort of AI model that can be customized to the individual scenario, to the individual system, to the individual process, whatever it is, you can build up a centralized model and then apply it to lots of different downstream domains. Models that are based on huge amounts of data. Well, I think that kind of ties in with some of the things I've said already. I think satellite data is certainly one of the really good examples here of we collect massive amounts of satellite data, and to just go through that and deal with it every single day is a very, very difficult thing to do. So trying to build models using that sort of data naturally fits into what makes a good machine learning problem. And finally, when you've got some underlying patterns that you can replicate and you can detect, you're trying to really understand what's happening within those data. So that could be taking some sort of clustering approaches and things, but again, it's a very data-driven approach. And I guess because I seem to keep on disagreeing with myself, I also need to talk about what machine learning can't do. Because it's not magic. It's not going to solve all the problems. A lot of it depends on the quality of the data that you have. As I said earlier, these systems will live and die on the quality of the data that we have. And there are problems that are not appropriate for machine learning. It's not the magic fairy dust that's going to come and solve all your problems. And please, whatever you do, if you've got bad data, don't just get an AI to generate more of it. So really, if you're then looking at trying to build something with machine learning, it all comes down to how you frame the problem and how you design the problem. And this is the ideal situation, right? We've got a bunch of data, we put it into an AI, boom, we've solved all the world's problems, we've got some profit. And the reality is that's not how it works. Sorry to break it to you. I've been trying it. The problem framing in machine learning is that machine learning is fundamentally an interpolative approach. It works on interpolation, not extrapolation. That doesn't hold for most other large-scale systems when you process data, because you'll design it based on some sort of deterministic path and you know what to happen. In machine learning, we're really trying to work out how you can take your problem and frame it as some sort of interpolative approach, which means that modeling and understanding the extremes of the data is almost as important as exactly what's happening in the middle, which is really annoying when most of your data follows some sort of bell curve or Gaussian, as most data do. But that means that you will always have less ability to represent things at the very far ends. And it takes a little, it's a very, very difficult thing to do, to work out how you take an extrapolative problem and frame it as an interpolative problem. But you really need to think about how you can transfer into a different way of thinking, into a different domain. And it's really all about how you can frame the problem in a slightly different way. So how do you find those outliers in the data and then represent them better within the data that you have to then train the model, and then it becomes a more interpolative problem. And then you can think about, from the AI side of things, whether you're doing AI terminology such as classifications, where you're making a prediction of something based on it being a specific class, where you're doing some sort of regression modeling, where you're predicting some sort of continuous number, where you're doing some sort of clustering. There's a whole bunch of AI specific or machine learning specific terminology for different domains and different ways of trying to frame your problem. There's a massive number of things you can do with it, and there's a whole bunch of approaches with when I don't have enough data or when I have too much data. It is a bit of a minefield. This is just one flow diagram that I stole off of sklearn's site that kind of gives you an indication at a first step, but there are much more complicated structures as well. But it's just to acknowledge the fact that the way you frame the problem will completely change how effective the method is. And so can you take this continuous number and quantize it? Can you try and break up so that you then have a more balanced and more representative data set? You also have the question of what sort of machine learning model should I use? Do I go and build this bizarre, this large scale neural network thing, or do I pick up some random forest modeling? And this I stole off of a paper from a few years ago, and this completely mirrors all of my experiences, and it's this little bit down here that is the most interesting part of this entire plot, in the fact that actually with the more traditional machine learning methods, the more deterministic methods, when you have fewer data, they perform really well. And it's only when you get into deep neural networks and larger models that you really need the scale of data for them to be any use whatsoever. So to that end, you need to ask yourself, do we have enough data? How much is enough? In the machine learning context, it's very, very hand-wavy. Sometimes people produce specific numbers, but how much is enough? And it's an impossible question to answer, but I can give you some intuition. The more complicated it is as a problem for you to understand, the more data you need to represent it. So can you get a child to understand this problem and they'll be able to do it in 5 minutes? Or do you need a full undergraduate course? Or do you need to have finished 3 postdocs before you can understand what this problem is and what might be feeding into it and be able to identify it in a graph? The more complicated that problem is, the more data you will need to represent that problem. What are your data limitations? What is your data quality? You're building a model based on data. So if those data don't represent a certain domain, you're never going to be able to achieve any model to represent that problem effectively. You won't be able to train a model based on a local water body and then transfer it to the Atlantic Ocean. You need to consider what the limitations of your data are. You can't extrapolate. And you can consider a whole series of different self-supervised, unsupervised, weak supervised type approaches. And what that fundamentally means is, how do we frame the problem slightly differently to learn from different sets of data? Some of them are designed to use data that are noisy. Some of them are designed to use data that don't quite make sense or have gaps in them. There's lots of different approaches we can take there. I also think it's important to acknowledge the bias within the data that we have. I think all data are biased. I'm not sure if that's a controversial statement or a statement that everyone should agree with, but it's a fundamental belief of mine that all data are biased. I don't think it's possible to get an unbiased data set. It's how we get the data. It's those data that we use that really are representing the biases that are included within the way the data are collected. But that means that gold standard data with the highest quality lab measurements have a massive amount of value. They're incredibly important. But so are high frequency, noisy, lower quality data, because then we have a lot more data with acknowledged uncertainties, and we can do a lot with them as well. I think there's a really nice analogy here with the medical industry. So you'll do a whole bunch of medical experiments where you're trying to understand whether a certain drug is going to cure a certain problem. And the gold standard is you sit in lab tests and you start mixing different chemicals and proteins together to see what the interactions are. And then the high frequency data is probably more akin to you're doing some sort of clinical trial, because people are randomly different from each other and we don't fully understand why. And we need to do both of them to fully understand what the effects of that individual drug are. And I think both of them have a lot of value. And so if we're not sure what the impacts of those high frequency data are, while actually doing a randomized controlled trial, collecting lots of data that have different biases, different known biases, but collate them all together, we can really help reduce some of those biases by aggregating large collections of data together. So we really need to think about how we can combine data from different sources that are from different levels of quality so that they can then be used together. This has all been a little bit abstract and things, so I kind of wanted to talk more about the aquatic systems data. I mean, there's a massive amount of different domains. There's physics, there's chemistry, there's biology, there's all the ocean-atmosphere interactions, there's climate signals. There's a massive amount of different types of data that we have, and all of them come with their own different challenges. There's different methods of observing them, there's different levels of uncertainty, and there's a lot of challenges within the data that we gather. You all know this. I don't know why I'm bothering to tell you. You all know this. In terms of using those data in a machine learning context, there's a load of barriers as well. The data scarcity. It's just very expensive and very difficult to go and get measurements of the ocean. It's just very, very difficult. And even in the middle of lakes, you have this three-dimensional thing with depth that you can't see a lot of the time. It's just very, very difficult to go and take those measurements. And those data will have gaps. But some of those data also end up in silos where it becomes quite difficult to access those data. And I think there needs to be things we can do to approach that. Data equity. I think there are certain parts of the world, certain oceans, certain lakes that are just undersampled compared to others. There are certain areas that are sampled incredibly, incredibly well, and others that are not. Sustainability. I think what I was thinking when I wrote sustainability is I was thinking of the sustainability of these observations that we are making. These observations are vital for our understanding, not just for AI, not just for machine learning things, for all the science that we do. And ensuring sustainability of those observations for long time series is vital to our further understanding of our planet. And from that, we can then go into how you might build an AI model that can generalize. How can you build something in one domain that might be able to apply to other domains? And that, therefore, you need to consider what the implications of that model are and what data it's trained on. And finally, trust in your machine learning systems. If we can build machine learning systems that we have faith and we have trust in, then they actually become useful tools rather than one way of posturing. But in order to get there, it's a bit of a maze. And there's quite a few different steps we need to take. And so I kind of came up with a few things that I thought were, to me, as a computer scientist attending an aquatic sciences conference, the issues that I've faced and the issues that I've seen. And it's not to say that all of these are complete issues across the board, but I think they are issues that need to be addressed in the community in order to really leverage the benefits of AI to the maximum effect. And one of them is data standards. We need to make sure that data are reusable. We need to encourage sharing of data, and data standards do improve data quality. This has been demonstrated time and time again in other fields. But that doesn't mean we need to go out and build new standards. I think we just need to unite under one banner and use the standards that currently exist. I think we need more fair data. I think data needs to be fair and publicly available. I think you need to be able to find it and you need to be able to use it, because I will inevitably use data that it was probably not intended for when it was first gathered, or I don't even know exists, but I might use it to try and understand some other part of an ecosystem. And I know that this could potentially be quite a controversial point with fair data. But what I have seen in medical sciences is all the pharmaceutical companies have agreed that actually it makes much more sense for them to start sharing all their data as fair and public, because they can profit more from it when they start sharing all the data amongst themselves. And so all of pharma and medical data is becoming more and more fair and more public. And I think if they can do it, I think we can also do that. Finish my mini rant, I guess. So the other thing that I think could be really beneficial is building some standardized data sets to benchmark. AI and machine learning communities love a challenge, love a competition. And every single time they do that, people put together data sets. This is a plot of a few different data sets and what the score was out of 0 to 1. And so the first couple of data sets are things like ImageNet, which was a sort of standardized, you've got an image and it's got some classification and you're trying to make some prediction, and it fairly quickly trended up. And so essentially they just created more and more difficult problems, which are these further on data. So there's squad things are, instead of just image detection, they're really putting paragraphs of text along with an image to try and explain it and describe it. And so you just end up with these more and more complicated challenges. And once you release a large-scale data set saying, here is a problem that I want to solve, here is the exact data that we need, you have fields of people who will just then jump on it and they'll go, yeah, I want to solve this problem. But I think it's really important that those challenges and those benchmarks come from this community. Because if you get AI people to define what that challenge should be, you're going to have something that's no help to anyone. It'll be a really interesting, fun challenge for them and a really nice puzzle, but it doesn't actually help our understanding. A good example of that could be I've seen a few underwater imagery people who, underwater imagery computer scientists who've taken a whole bunch of images of fish and they've done all this fancy thing where they can detect things, and then you give it to a biologist and they go, yeah, well, that's no use to me whatsoever. What I actually need is this, this, and this. And so I think we need to be defining what those benchmarks, what those challenges are with large data sets, making them available, and then the communities can take them up. And finally, I wanted to talk about, let's say finally. And at this point, I wanted to talk about trying to understand what's happening within these AI models. Like I said, I think trust is really important in these systems because it's very easy to build something that looks like it does a really good job, and then the moment you apply it to somewhere else, it gives you a totally wacky result. And I think we really need to interrogate what's happening within these black box models. So when we learn from something, we really need to interrogate why it works and how it works and understand what's happened. And there's a couple of fields that are doing this. One is explainable AI and one is adversarial AI. And these fields within the AI communities are really trying to explore how you explain what that thing has done, what the AI model has done, or try and break it, try and find use cases. So in the top example here, you've got a picture of a panda, and they essentially just built an AI that just says, how can we possibly change the label of this? Generate me some noise that I can add as 2% to this image so that it will completely change the output result. So they're really trying to take something and hack it apart and say, well, how can I make you think something else? And by finding a way of breaking it, we can then find a way of fixing it. The other option is that you just take two images and you kind of very carefully blend them together. And I think there's a bunch of other really interesting examples with this, where you can take something as simple as an apple, and then you can get it to rebrand as an Apple iPod. I think it's a really funny example, but I think it's also, these are, I believe, images. Well, I think this was an image originally that was similar to the ImageNet approach, where it gives you a classification of different things. And an iPod being one of the labels shows just how old this data set is if that's one of the classes, because I don't think we have many iPods being made these days. But the point is that you can then take these approaches to try and hack your AI model and try and work out why it's not working. And then there's explainable AI. And explainable AI is another field of research. I didn't really find any good pictorial images, but essentially it's just, there are three different entire branches to that field of research. The explainable data is really, what was the data that was used and why? Why do we choose those data? How do we, so really exploring the source data and what happens if you make perturbations in those data to try and understand what the output might come. And there's toolboxes that allow you to do that really, really easily. Explainable model AI, explainable AI for models, is where you really start looking at what's happening within that specific model. So you might be looking at individual layers of a neural network and visualizing things and trying to understand what decisions are being made at what individual point and really understand the individual components. And the explainable prediction side of things is, well, why was that decision made? What specific input features were most important to that? What specific weights in this model, and why is it made that? And can you justify to me why that decision was made as an output predictor? And I think with doing these things and engaging with those fields and those communities and using those tools, we can begin to understand a bit more about these different AI approaches and hopefully begin to develop some sort of trust in them or complete distrust in them because it's completely disproven or giving you some absolute nonsense and noise. But it's a way of measuring whether or not we should trust this system. So I guess just to summarize, I think we need to solve data access. I think there needs to be cross-disciplinary collaborations. I think people in the AI community would be very, very happy to work with people who actually care about the planet and want to do better things. There are a lot of people who do, but sometimes they just don't know how. And building standardized data sets and benchmarks so that they can do that, or engaging in those conversations, I think could be very beneficial. And increase domain-specific data. Finally, I quite like this cartoon. Because sometimes a machine learning system is just a big pile of linear algebra and data thrown together and you keep on trying. And I can completely understand, I wouldn't trust that either. But I think there's a lot of things that we can do to help develop that. With that, I will say thank you. And I believe I have some time for questions if there are any. Well, I've either bored you all to sleep or oh, hello.
Well, there's a lot of literature out there, and I asked the computer what it could tell me about how Daphnia, my favorite organism, responds to oxygen. And I was actually looking for a literature search. It gave me an answer, and it gave me an answer I liked, but it didn't tell me what paper it took it from. And then it just had a whole long list of papers. It didn't occur to me that maybe it was in order of relevance. I assume that literature searches either are in order of publication date or author's name. If I keep asking, will it maybe give me some clarification?
I assume we're talking about LLM chatbots?
I think I was in Google. I just asked. It gave me an answer I like.
So, yeah, let's start by making clear this is my opinion. My understanding is that the first couple of AI systems, when asked to provide a reference, they said, yes, not a problem, here's a reference, and they spewed out something that looked very plausible. It came up with people's names that were appropriate, it came up with conferences that were appropriate, and you go and search for that paper and it never existed. Because it knew what a reference should be, but it didn't realize that there was a physical association with the real world. Because it just saw a reference at the end of a paper and it went, oh, that's how you make it look proper. And it didn't understand that that actually links to something that really exists. I think that some of those models, when you ask them now for references, they say, I'm not allowed to give you references, which is a very easy way of getting around not having to solve that problem. And there are some models that are beginning to look at how you find those references. I don't think there's a way that I could solve that problem, but I believe there are one or two models that will provide more appropriate references, but I don't want to give specific ones because I can't, I wouldn't be able to say with confidence.
Thank you for your talk. You spoke to the importance of cross-disciplinary conversations, and as someone I think who does that a lot in your work, I was wondering if you could give us as a sort of community Optimum data collectors and having that domain expertise, what you see as barriers for effective communication across these disciplinary boundaries uh, as we're trying to build these standardized data sets and benchmarks.
Um, I think I'm trying to work out. I want to depersonalize this first of all. I think your data are quite, well, they're complicated, right? And that's because the problems you're trying to solve are complicated. And so I think there's opportunities to approach simplified domain problems where you essentially just say this is a problem that can be solved, but we haven't solved it yet, and clearly define that problem, because I've spent quite a few years talking to different people, and unfortunately different people have different opinions as to what those problems are, which is completely understandable. Everyone has their area of expertise, and that is the field that they think should be prioritized. And I'm not saying any of them are wrong, it's just that you need, I guess it's the same as when you go and try and teach a class to some undergraduates. You need to make something accessible, and you need to make something that you can engage with. And you need to say, well, I have this data, and here is a problem I'm trying to solve. And even if that doesn't solve all the surrounding problems, but it gives you context, it opens that dialogue. I'm not sure if that answers all of your question, but
I have a question that I think is somewhat related, but a little bit more focused. So, I'm intrigued by this idea of these challenge data sets to present. And there are multitudes of data sets that we all deal with and work with. So I'm wondering, what are the characteristics of a data set that make it interesting for one of these AI challenges versus like interesting to us because they're complicated or related to questions that we're interested in?
that's a good question. I think, well, so first of all, it needs to be easy for anyone to use and put straight into an AI model. So there's a bit of data wrangling that needs to be done. But I think something that is, something that is difficult enough, which is kind of the same as do you have enough data? Something that we have massive amounts of data for and is challenging, but it's not something you can solve in 20 minutes. So I think there's maybe a collaboration with some AI researchers to actually develop that and maybe go through a process of let's try and create a problem that works and makes sense. Because it needs to be something that's difficult but achievable. And I think that's a very difficult boundary to define much beyond that without knowing any specifics of what you're trying to do, I guess. Sorry.
Great. No, that's helpful. Thank you.
Hello. Thank you very much for your talk. It was extremely accessible, and I appreciate that a lot.
It's very easy to add lots of big, confusing AI words, but not easy to explain them in English.
So I'm going to ask an annoying question. What does good quality data mean to you? Is it something that's very complete or feature rich? Or do you define that in terms of how well the stuff that comes out of the other end matches with your preconceived notions with the data?
To me, good data is data that is representative of the more general problem, which I'm not sure is any of the ones that you offered up, but I think it's something that is more broadly representative of the entire problem. If there's additional features, if it's feature rich, I think that can have value, but I think it's more important that it is fully representative of an entire domain, of an entire problem that you're trying to solve. It's not just the really high values and not the low values, or not just when it's sunny but not when it's cloudy. I think you really need, in order for it to be useful and applied to something downstream, you need to be able to represent all the different ends of the spectrum, I guess.
So I suppose the question is, to us, how should we be defining our problems to be as generalizable as possible to machine learning folks?
But yes, but the question from me to you is, well, what problem am I trying to solve? Because I'm just playing around with some stats and some data to do something, and I can create a fully artificial problem with some fully artificial data and then have a great time with it. That's fine. But if I want to actually solve actual problems, it's your problem that I need to solve.
Okay, thank you.
I'm being told that time is up. Okay. I am here for the rest of the week, so you are welcome to come and grab me and have a chat some other time as well.
Thank you for your talk. It was honestly super interesting to hear about like AI and machine learning within the realm of ocean sciences. And this question might not be directly so much towards it, but just out of pure curiosity, as someone with a computer science background, with something like advancements in like quantum computing coming up on the horizon, how do you think that would advance machine learning in the realm of any science field? And with the distinct challenges you already mentioned today, how do you think we're even prepared for something like that?
So quantum computing is a paradigm that we're kind of just dipping our toes into. Fundamentally, it works on a couple of key principles, but a lot of the algorithms were developed in the 80s and 90s. I mean, a lot of the machine learning algorithms, a lot of neural networks were all designed in the 80s and 90s as well. So it's just that we've had the compute power that have really accelerated in the past few years. I mean, I think it can accelerate some compute, but fundamentally, we're the ones that need to define the problems that we want to solve. And whatever tool and whatever technology we're going to use, it doesn't matter if it's a linear regression or some complex quantum system. I think fundamentally what we want to do is understand what is happening more with the data we gather and the systems that we observe. So I would view that in the same way as I view machine learning, which is a tool to do some interesting research.
Thank you.
But that's just one man's opinion. Yeah, thank you very much.